session with Miguel Ratis Laude from IMPA, who will speak about David regularity of an extension of Yokot's conjugators.
Thank you very much. Is everyone hearing me fine? So before getting to the actual point of the talk, as it says, it's regularity of a conjugating map between critical circle maps and the associated rigid rotations. I want to inspire everything that I'm going to talk about with some actual complex dynamics, because things are going to get analytically very quickly. So I'm going to start from the classical construction in complex dynamics, which is the Douadiji surgery. And it works in the following way. We start with this one parameter family of rational maps. And they have the property that the circle is forward invariant. And when restricted to the circle, this is actually a homeomorphism. It's going to be analytic because it comes from a rational map. And it has a single critical point at 1. So we are in the nice setting of analytic critical circle maps, for which Yokot showed that whenever the rotation number of this map is not rational, then we can find a homeomorphism that conjugates the map with the rigid rotation of angle theta, theta being the rotation number, right? The point of this construction is to start with this nice map that we understand. This is called a Blaschke product, and we can do a lot of nice computations for those guys on the side of complex dynamics, and trying to get to a more complicated object on the other side. It's going to look simpler, but it's more complicated to understand. And the whole idea is that because we have the conjugation with rotation along the boundary of the disk, along the circle, we can extend this conjugation to a homeomorphism of the disk, and then just swap the dynamics of whatever the Blaschke product was doing inside of the disk before for something that is conjugate to the rational rotation. Right now, this is only a topological dynamical object, but it has the following interesting properties. 0 is going to be an indifferent fixed point, so it's a fixed point where the action is an irrational rotation, and this linearizable line here just says that I'm conjugating the action at 0 with the action of the rigid rotation in a neighborhood of it, and indeed the neighborhood is in the entire disk. We still have that infinity is a super attracting fixed point. By super attracting, I mean that it is critical, essentially, so it's fixed and critical. That's true just because of, it's true for this map, and we're not changing anything in a neighborhood of infinity. And the final map that we get is of degree 2. So these things imply that if I can straighten this thing, so if I can put it in if I can conjugate it to something that is actually holomorphic, then that holomorphic map is going to have essentially all of these properties as well, which forces it to be on a very specific shape, exactly this one here. So if this topological object that I constructed can be conjugate to a holomorphic object, then this object is exactly this polynomial. And why do we care? It's because for that object that I constructed, when I look at its Field-Juliat set, which is the set of bounded orbits, so all of the orbits that are not going to escape to infinity, I have that the boundary of this set is going to be locally connected and have 0 Lebesgue measure. That's for every irrational number. And this is very much not a property that is going to be true for every irrational number on this side, and it's much harder to show it on the case of the polynomial. The shape is a lot more complicated. I mean, for these guys, the Field-Juliat set is going to start with the disk where everything behaves like rotation, and then you're going to have pre-images of the disk that are going to look like these tear-shaped domains that just glue together in a certain combinatorial sense that depends on the rotation number and etc. I'm not good enough with drawing to go beyond the first pre-image, sorry. But the polynomial is going to have a very fractal structure on the domain where you have conjugation with rotation. So we have a topological model where we can prove nice things about the set that we are interested in. The Julia set in complex dynamics is essentially the set where chaos actually happens, so it's the interesting set to study. And these properties are going to go through. I mean, the zero Lebesgue measure, you need the conjugation to be nice enough, at least to preserve zero measure sets. But other than that, the local connectedness is just up to a homomorphism. So the original idea, it was the idea of Douai-G, and I believe it was G that actually wrote it formally down, is to use the theory of quasi-conformal maps to realize what's called a quasi-conformal surgery. So I'm not going to go into too many details, especially because we don't actually come back to this, but essentially, this is the definition of a quasi-conformal map. The important thing is that it's an orientation-preserving homomorphism where the distortion of the map, which is this quantity defined here, is bounded almost everywhere by the same constant. And the point of these maps is that if that extension that we took here for the construction, the extension of the conjugator that is defined on the circle to the disk, if that extension can be taken as quasi-conformal, then it turns out that the whole map that we get in the end is what's called quasi-regular, and that means it can be straightened into a holomorphic object. And it's a theorem of Hermann-Chiviontek that this conjugator will admit a quasi-conformal extension if and only if the rotation number that we started with is of bounded type. The reason why we have an if and only if statement here is because we understand very well the boundary behavior of quasi-conformal maps. They're called specifically quasi-symmetric maps. I'm not going to get into too many details as well. But it's a definition that does not depend on the actual map on the disk. So that allows this if and only if statement. And more recently, and by more recently I mean around 2008, Peterson and Zaccheri extended this result to a much larger class of maps using a different kind of surgery. So as I said, this is an if and only if statement. So if you want to do quasi-conformal surgery, that's the best we can do. We only reach bounded type rotation numbers. By the way, just to define, if you don't know, bounded type, if I write my rotation number in its continued fraction expansion, bounded type just means that all of the terms in the continued fraction expansion are bounded by a uniform constant. So what Peterson and Zaccheri used was the theory of the V maps, which are very similar to quasi-conformal maps, but now you allow the distortion to explode, but in exponentially controlled areas. And we can still do the same. If that extension that we took before can be taken as a V map, then we can perform the V surgery and straighten everything to a holomorphic object. There are some very nasty technicalities in here because we actually have to, you have that the map is the V in here, so you have exponential control of areas here, but then you're going to sort of spread this behavior by the dynamics through all of the preimages of your disk. So you need to know that those preimages also have their areas decaying exponentially. In essence, that's the technical part. But with that, they show that the Yacost conjugator admits a V extension whenever theta satisfies this relation here. So the coefficients in the continued fraction expansion are allowed to explode, but not in arbitrary ways. I mean, they can explode very fast. They can explode like exponential of root n, which is a huge difference from bounded type. It actually goes from a zero measure set to a full measure set. But the statement is lacking the only if part. And the reason behind that, and the reason also why I say it's a Yacost-Peterson-Zaccheri result, is that they use the construction of Yacost. It is, I'm going to call it the Yacost extension of the Yacost conjugator, and I'm going to define it very soon. And the thing is that they show that in that class, this extension is the V. we started trying to work whether the if and only if could be proved more generally. Turns out that's a very hard problem. And it goes back to essentially that question that I said. Quasi-conformal maps, they have a boundary behavior classification. They are quasi-symmetric. The V-maps, we don't have literally any sort of statement like that. There are several necessary and sufficient conditions. There is not an if and only if statement that characterizes those maps on the circle. So the boundary value of the V-maps on the circle. But for this extension process, and I should have said this at the beginning, sorry, this is a joint work with Luna and our collaborator from the south of Brazil, Lucas Oliveira. What we managed to show is that this extension is, if the extension is the V, then we are in the Petersen-Zacchetti class again. So at least for this extension process, we are capturing very well the behavior of the regularity of this extension property is capturing very well the behavior of the arithmetic behavior of your rotation number that you started with. And indeed, we also did essentially the same computations for the inverse, and we find a different sort of condition here in the end. I'll talk a little bit more about what that means, but don't worry too much. It's complicated. There's not a very nice way of writing it, but for now, that's it. I will say it's very much different from the condition for the Petersen-Zacchetti class. And the point here is to observe that the V-maps don't necessarily have the V-inverses, which is another big factor of complication with working with those maps, actually. So, okay. I will spend basically most of this talk explaining to you what this Joukow's construction of the extension of the conjugator is, because understanding it well is the basis for proving anything regarding it. And it follows some deceivably simple steps, but the ideas behind them are very deep. So first of all, we're going to just lift everything to the upper half plane because it's easier to write things there instead of in the disk. So instead of thinking of a map on the circle, I'm always going to think of a map on the real line that is going to be one periodic. And I mean, 0 is going to be my critical point of choice because I can put it anywhere. The first step is going to be to construct some grids on the upper half plane that are based on dynamical partitions of the real line induced by the map F and the corresponding rotation, so that we can map one grid to the other in a piecewise affine way, and then just worry about extending those maps within each cell of the grid. The construction looks very much like Carlos and Box's constructions, if any of you have heard of it. If you haven't, it's not exactly like that, so it's not too important to know it for right now. So as I said, we're going to put the extension to be piecewise affine on the grid, and then in each cell, we're going to extend this map. But piecewise affine maps are still too general, so we're going to, observing the distribution of points in the partition, exchange this problem for one where we are extending just a map that is piecewise Mobius, but specifically it only has 2 pieces. So we'll get there. I don't need to draw it right now. OK. And finally, it's just the matter of computing bounds on the areas and the distortions and etc. OK. So first part, as I said, we're now thinking of analytic one-periodic homomorphisms of the real line. We're asking for 0 to be a critical point, and we're fixing its rotation number as being theta, right? The dynamical partition that we're going to consider is just looking at the orbit of the critical point up to the qnth iterate, and then this plus z here just means that essentially we're looking at the orbit in the circle and then lifting it to the real line. The good thing about those guys is that we understand very well how they partition into one another. Whenever we take an interval that started at level n of the partition, then it's going to be subdivided into the next level into something that depends on the term in the continued fraction expansion. So it's an plus 1 or an plus 1 plus 1. The actual number doesn't matter. The thing is that it's comparable to an plus 1. And this can be observed just essentially by drawing out what things should be. So intervals of a certain level are going to appear in two forms. Either they are some iteration of, here I drew everything in the circle, that's why there's a 1 here, sorry. One of the extremes are going to be one point in the orbit, and then the other one is going to be a next closest return. So if you remember, I should have actually defined this Qn better, sorry. The numbers Pn over Qn are just truncations of this continued fraction. So when you add up to n over here, you get Pn over Qn. Qn is the time of closest return to a point. So whenever you're looking at the dynamics of this point under rotation or under a map that has theta as its rotation number, you have the point over here that I was taking as being 1. It's going to have a certain return here at time Qn. And then the closest one to it will be, after this, will be Qn plus 1. And then they just accumulate on the point alternating sides. And that's true for any point. You don't have to take the critical one. So if you take something in the orbit of the critical point, that's also true. So if the Qn minus 1 return is on this side, then the Qn return is going to be, so let's see. If the Qn minus 1 return is on the left, the Qn return is going to be on the right. So starting from this point and going and looking at its Qnth return, it's going to be closer than it was to this point. So you start subdividing the interval until you reach this part here, and then looking at the relation that Qn plus 1 is an plus 1 Qn plus Qn minus 1, which comes very classically from the theory of continued fraction expansions. We get the point that is right next to this iterate. And then you count how many points you got partitioning this interval. You will get, in this case, an plus 1. And you have a separate case where the interval starts looking like this, but the process is exactly the same. You just start looking at the first iterates, at the first returns, until you reach a point where it's going to be too close to this. And in this second kind of intervals, you get an plus 1 plus 1. The important part of all of this is just that the number of these points is related to the arithmetic of your theta. And that's going to be important because that number is essentially going to be the multiplier of a certain map, and it's going to be involved in how the distortion appears. So how do we construct the grids that I promised before? We have our points in the partition Qn. We're going to look at the average lengths of the adjacent intervals that have that point as a common boundary. That's going to give us a height. And then we just look at points based at points of the partition with that given height. The reason why we're doing this is because we have good controls on the lengths of intervals defined by a dynamical partition. Then we expect to good control the geometry of the cells of this grid when we're going to do the full construction of the extension. So now we're going to just connect 2 points on the upper half plane whenever they are based at the same point of a partition, or whenever they are based at the same level but by 2 adjacent points. And obviously all of this construction also happens for the rotation. You get actually 2 homeomorphic grids, and because we're joining everything by straight line segments, you can just send one grid to the other homeomorphically in a piecewise affine way, right? So that's the heaviest part of the construction. That's where most of the combinatorics are going to go. Now it's a matter of looking at this messy picture and simplifying it to a picture where we can actually say something without going insane, because the shapes of these cells can be very, very bad. But the thing is that they are controlled in a very specific way. By that I mean we have a priori bounds on the dynamical partition. As a result of Hermann-Schwientek as well, it just means that whenever you have two adjacent intervals defined by a partition, their lengths are comparable. By comparable, what I mean is, where's the wine? By comparable, what I mean is the ratio between these two lengths is going to be bounded above by some constant and below by the inverse of that constant. And that constant is not dependent on the intervals, on the level, on... It can be dependent on the map, but nothing, it's not dependent on anything that we actually vary along the proof. Because the heights of the points that we chose for the grid are averages of lengths of adjacent intervals, they are also controlled, and we can show that the cells are going to have a good geometric control. And what I mean by that is essentially we can map them to sort of standard squares. Let's take the one where the basis is -1 to 1 and a height of 2, obviously. And we can always choose those maps in a way that the distortion, they are quasi-conformal with a distortion that is also universally bounded. So if you compute the distortion of these maps is going to be bounded by some constant that doesn't depend on the cell, that doesn't depend on n, that doesn't depend on anything except maybe the map. Okay. The good thing is that we can actually do this in a bit of a specific way, just by being a bit careful on how we map these things. We can map the cell to the square in a way that the distribution of these bottom points here, that are the coordinates, so the x coordinates of the vertices at the bottom of the cell, are preserved on the other side. So we are looking at the same distribution of points on the other side. And now we need to understand finally how these points distribute to understand how we're going to actually get an extension to the full square. So just to take a little detour here explaining, we have some cell here that we're uniformizing in the square, and whatever distribution the bottom vertices of the cell had is going to be preserved here on the other side as these bottom points. We have the distribution on the case of the rotation, which again also can also be adjusted into a square, and then we preserve the distribution of points here at the bottom. So now the problem is mapping one square to the other in a way that this distribution of points is sent into this other distribution of points. And in each piece of interval here, you have an affine map. So it's a piecewise affine map here at the bottom. And on the sides, it becomes identity because it's the same square that we're looking at. So how do you send affinely the segment between 0 and I to the segment between 0 and I? It's identity. So okay, what is the distribution of those points at the bottom? For rotation, it's very simple, since they are just points in the orbit of 0. And rotation, well, we're lifting on the real line and just x by translation by the same number. These points are very uniformly distributed on the other side. So indeed, the two adjacent points inside of a bigger interval are going to be essentially as far apart as the size of the whole interval divided by the number of points you have in there, which is comparable to an plus 1. On the side of rotation is where things get more interesting. This is a result of Yacoz, and it essentially relies on the fact that, as I mentioned before, actually better to go back to the image here. As I mentioned before, you get partitions of these intervals by looking at Qn returns of your point. So the dynamics of Fqn on this interval sends each of these dividing points to the next. And Yoko's defined that as being what he called almost parabolic. The almost parabolic behavior is just when you look at what the lengths of these maps can have, you get exactly a parabola because they have this quadratic behavior here. So what I'm trying to draw in the picture here is on the side of rotation have a uniform distribution of points, that's fine. On the side of the dynamics, these points start accumulating at the center because the central pieces have shorter lengths than the outer ones, and that behavior is quadratic. These lengths behave in a quadratic way. So if you were to draw at each base point the length of the corresponding interval, the image you get is something that looks like a parabola. That's why it's an almost parabolic map. And so with this, we are looking at a distribution, looking at the inverse is easier. We're looking at a distribution that started uniformly and then got accumulated at the center of the interval and ran away from the extremes. So the great idea for the extension inside of the cell is to replace the dynamics of this piecewise affine map that is sending this interval to this interval, this distribution of points to this distribution of points, to one where you just have two repelling fixed points at the extremes of the interval and one attracting fixed point right in the middle. And that's where the piecewise Mobius action is going to appear. We're going to use this family of Mobius transformations right here. The form of them is not too important. What's important is they act on the interval 0, 1, fixing 0 and 1. 0 is going to be attracting, and the multiplier actually depends on this parameter a. It's going to be 1 over a. And 1 is repelling with multiplier a. And you have a sort of quadratic behavior as well on the sizes of intervals. If you think about doing a uniform distribution on one side and seeing what the dynamics does to it, it essentially sends uniformly distributed points to points that are spaced in that quadratic manner as well. So the idea is to put one of these maps, so not exactly this, but conjugate to this, between -1 and some central point in the distribution, and another between 1 and that central point in the distribution. So what you get now we started with this piecewise affine map here. We're going to actually extend the inverse, and because we're looking at quasi-conformal extensions of things, at least within each cell, it's okay to look at inverses. The constants that bound the distortion of the inverse of a map and the map itself are the same. So we're going to look at the inverse that does that. It's a matter of we apply this piecewise Mobius map, let's call it zeta here. We get something that distribution-wise looks like this, and that there's some effort to showing that the map that sends this distribution of points to this one is actually going to have a nice uniformly bounded distortion quasi-conformal extension as well, but you can do it. And so the whole problem just becomes an extension of this piecewise Mobius map here. And the idea now is to look at each half where you act as a Mobius map independently. The point is that because you have the action of a Mobius map, you actually have a smart little trick you can use. Let's say this is the midpoint where you're breaking the two Mobius maps. Those Mobius actions will have real coefficients because they're going to be essentially automorphisms of the upper half plane still. So not only do they send this segment of the real line to the appropriate one underneath, they also fix the geodesic connecting the two extremities of this interval. Now, you can do a change of coordinates sending the repelling fixed point to 0 and the attracting fixed point to infinity. I actually pointed them in the other way. Depends on what side of the drawing you're looking, actually. But anyways, you send the repelling fixed point to 0, the attracting fixed point to infinity. Because you started with a Mobius transformation, you're going to end with a Mobius transformation, and that forces it to be the action of multiplying by the multiplier. So this is a linearizing coordinate, in a sense. And this sort of half disk here is mapped to the quarter plane, just because geodesics have to be sent to geodesics. And now what you're going to do is use logarithmic coordinates to uniformize this quarter plane into a double strip, where now the action of your map on the real line becomes the action of translation by log of the multiplier on one of these lines here. So the problem started as this. We have the action of the Mobius transformation from this interval to this interval. We encased it with the geodesic. And now all I want to do is use these coordinates, use this nice strip where we can interpolate things, to have the action on the geodesic be just identity. And inside here, we're interpolating between the Mobius map and identity. We're going to do the same thing on the other side. And then on the outside, when we're looking at the whole cell, we just put identity everywhere else. And when you do that, in here, it's just interpolating between translation by log A and identity. You get a map that has this estimation of distortion. The distortion of the map will behave exactly as log squared of an plus 1. That's a computation. You can do it, just not the most important part here. The important part is that you get an estimate on the distortion that depends on the expansion of your number in the continued fraction, right? So you have control of the distortion. Now you need a little bit of control of the area, but that just comes from, again, a priori bounds. If you do some more work, you see that well, here I put the heights of the points. It's also the lengths of the intervals in the partition. They are bound above and below by exponentially decaying sequences. So you have a good control of the lengths of those intervals, which is, in a sense, the areas of these cells. And that's how Petersen and Zakhetti originally showed that when you are in this class of log squared an equal of root n, then your extension is the V. Basically, you just look at when can you explode beyond log squared of an. It's whenever you are at level n or deeper. And then all of those cells are going to have a height that is being controlled by something that decays exponentially. The idea is just that. But that doesn't fully work for an inverse argument immediately, because a priori, whenever you're looking at the distortion of this map in a cell, it could be concentrated at surprisingly small areas, for instance. And if that was the case, then that extension being the V would not give us such a tight control on the actual rotation number on the other side. But we actually have a good property about that, because whenever we look at the area where our distortion is essentially, here I'm just taking lots of abuses of notation, but essentially when the distortion is high enough, comparable to log squared of an plus 1, the area where that happens is comparable back to the area of the whole cell. And that is essentially just by the nature of the extension process here, these sort of geodesics here cannot disappear simply. They occupy inside of this square a constant proportion of area. And because we're distorting things by uniformly bounded distortion quasi-conformal maps, these estimates don't disappear. So we still have that the area where the distortion is behaving essentially as log squared of an plus 1 is comparable to the area of the entire cell of the same level. And the area of a cell of a certain level is comparable back to something exponential in the bottom, which comes basically from this control on this side. We can get exactly the other way around. And oversimplifying the computations a little bit, but in essence it's exactly this. This is coming from just looking at exactly that. So we're taking the area of the points where the distortion exceeds log squared of an. Let's put an, just to simplify. The V property is bounding this by above. Let's do everything just comparable here. So this just means I'm ignoring constants that should appear in front of things. It's fine. So you get something that is like exponential of minus some constant times log squared of an. And this here is then comparable to the area of a whole cell, which is then bounded below by some exponential factor, and then just take logs on both sides, and you get exactly the control on the ANs back. Okay, so that's how you go back to the arithmetic properties of your rotation number. But now you just have to, the distortion control, as I said, is the same for the inverse of the map, just because when you're looking at distortion, it's the controls are always the same whenever you're going forwards or backwards with the map. Sorry. The thing is the area control now. So if we want to understand the regularity of the inverse of the Yakoz map, what we have to look is at the control of the area on that side. And I actually think I forgot to include it in the slide. Sorry. The control of areas on the other side. So remember we reduced it essentially to control of the sizes of the intervals of partition. And we're going to have above something like 1 over qn, and below something like 1 over qn squared, whenever I is a partition of level n. Those are very explicit computations because we're just looking at the rotation partition this time. And to estimate these guys, we start from, we start from that equation that I wrote before on the board. Using a little bit of induction, you can find these two inequalities here, but you have to get them a little bit better because if you have long sequences where AK is equal to 1, this lower estimate here is telling you nothing. So you change it just with a clever use of some quotients of Fibonacci numbers, you get a better estimate on the other side. And that's essentially where that hideous condition right at the beginning came from. So when you do the essentially same computations, you're going to get this guy over here. How much time do I have, so? 1 minute, sorry. I just want to say this class is strictly different from the other one. In fact, you're going to be the V, whenever the Yakoz extension is the V, the inverse is also the V, which is surprising. Generally, that does not happen. And the inverse is the V for a class that is essentially in between that of log squared of an equal O of root n, which was the Petersen-Zacchetti class, and log squared of an equal O of n. I don't have much time to talk about optimalities of those things, but I'm going to say just briefly, it's really hard to say whether an extension process, especially one that involves the V maps, is optimal in any sort of sense. But this one is at least within that cellular level. So if you start with all of the same setup, and then you only look at extensions within the cells, that's the best you can do. So you cannot get better there. It's a lot harder now to justify if you could get, for instance, a better partition. And just another observation is that when you look at the approximants of your map that are piecewise affine on the outside, sending essentially dynamical partitions to dynamical partitions, we can estimate what the quasi-symmetric constant of those guys are as well. And when you look at classical extension processes, that extension process of Yakoz is actually surprisingly a lot better than the classical ones usually are. They usually would go around the same order as the quasi-symmetric constant or even worse. The Yakoz extension one is log squared of that. So it's a lot better than what you would usually expect. And that's all I had for today. Thank you very much.